motion has to be transmitted from one shaft to another shaft. So you have belt drives, gear drives, and so forth. So we'll talk about the defect frequencies in these drives. Then some examples. So I may, since I'm from nuclear engineering department, I may talk about vibration monitoring in a power plant. Okay, simply speaking, vibration is nothing but the motion of a body somewhat away from its normal behavior. So if you have a shaft, a rotor rotating, and if the rotor is not rotating properly, if there is imbalance or misalignment, then the system is going to shake. You might have noticed when you drive your car, if something is out of balance, and the wheel is going to shake a little bit. That's because there is imbalance in the system. So it is caused by some sort of variation of the motion from its nominal position or normal position. It could be a rotating machinery or other types of, doesn't have to be just a rotating machinery. You can have stationary devices that can also vibrate. It says vibration occurs when the system is subject to internal or external forces. So the cause of vibration is some kind of force acting on the system, right? This force could be internal. Internal means if a pump is connected to a motor, the pump is running, and if there is vibration, that's kind of internal to the system. External vibration is caused by forces coming from outside. So if you have a large vessel sitting here, and if I have water coming and hitting this vessel, it's going to vibrate. So that's kind of a forced vibration or flow-induced vibration coming from outside. If an airplane is flying and you have turbulence in the air, then the plane is going to shake a little bit. So that is kind of externally induced vibration, right? So there are lots of causes of vibration, both internal and external. Then he talks about some examples of what is causing this. We will get into that a little bit later. Okay. This is an example of a shaft. It's a little bit exaggerated. You don't see so much variation in the size. So this is a shaft that is rotating inside a sleeve. So these type of bearings are called sleeve bearings or journal bearings. They are not very common. They are mainly used for systems where you have slow speed and heavy load. Okay. So what this is showing is the shaft here. The center of the shaft and the sleeve is right there, and the shaft is a little bit off the center. And this may be caused because of the oil. This gap here is filled with lubrication oil. So if the clearance or the gap is large, then this oil is going to shake this sleeve or the shaft. Then you can have a little bit of vibration caused by movement of this shaft around its center line. It's a little bit off center, so it's going to move around, and also it may do a little bit of sloshing. It's not going to rotate properly. So this is one cause of vibration. You can also have vibration if the bearings, if you have a motor and the bearing is not supported properly, you have loose bolts, then when the rotor rotates, the bearing support is going to shake a little bit. So that can cause vibration. And there are other causes of vibration. We'll get into those. Then it says here, why do we do vibration analysis? It's one of the more common tools for condition-based maintenance. That means you're looking at the condition of the machinery based on measuring certain things. That measurement must reflect the fault in the device. So if there is vibration, that's kind of reflecting some kind of fault, right? So it is used in condition-based maintenance or predictive, some folks call it a predictive maintenance. Vibration analysis is somewhat non-intrusive. That means you don't have to damage the equipment in order to find out what's going on, right? You install the sensors on top of the machinery, and you really don't interfere with the performance of the machinery. So it's non-intrusive or non-evasive. You look at both time domain and frequency domain signatures. So when you measure the vibration using certain sensors, you get some signals coming out of these sensors, and the question is, how do you interpret these signatures? Okay, what are we trying to measure or predict or detect? In general, if you are a serious condition monitoring person, you may want to combine several of these technologies: vibrational monitoring, loop oil analysis, infrared monitoring. Infrared monitoring is mainly for detecting any change in the temperature distribution in the system, right? You are trying to measure the temperature or looking for any hot spots in the machinery. So you may want to combine these techniques so that the combined way of analyzing or looking at the system would be more effective than just using one technique. Then it talks about the variation of the energy in the vibration signal at different frequency ranges, may be related to specific problems. When a machine operates, there may be different frequencies because of various types of anomalies or faults. So you may be able to identify, if I can measure these frequency components, I may be able to identify, okay, what is causing this frequency change, what is causing the other frequency change, and so forth. So I may be able to detect the fault or diagnose the fault. As I mentioned earlier, vibration analysis is made both for rotating machinery as well as stationary components. You are familiar with rotating machinery, all kinds of rotating machines, pumps, motors, compressors, turbines, generators, anything that has rotating shaft is a rotating machinery. Then it also talks about rolling mill stands. If you go to Alcoa plant here, Alcoa plant has several rolling stands, and each of those rolling stands, by definition, is going to rotate. The main shaft is going to rotate, and it's trying to reduce the thickness of the sheet to get thin sheet. So a lot of rolling machinery in a plant like that. What about the other structures that are not rotating? Aircraft structures, pipes, pressure vessels, and so forth. So there are a lot of other stationary devices, boilers and pressure vessels. All these things may vibrate because of flow induced or something coming from outside, external forces. This is an example of frequency. I mentioned frequency. I'm sure you're all familiar with this. If I say something has a vibration frequency of 10 hertz or 10 cycles per second, that means something is changing 10 times in 1 second. So this is an example of a simple sine wave, right? There's only one frequency in this sine wave. So if I take this sine wave and if I compute the energy in the sine wave, what do I mean by energy? If I just square this sine wave at different points and add them all up, I get a number. So that average number is like the energy in the sine wave. But notice that energy is only at one frequency, right? Because this sine wave has only one frequency. So if I make a spectrum or a plot of the energy, frequency, energy versus frequency, okay, you just get 1 point. Because there is only one frequency and the energy corresponding to that frequency, whatever that is. So you just get 1 point. So this is a very simple frequency spectrum. It's very easy to interpret this, right? What if you have several frequencies added up? Notice this is an example of adding 3 different sine waves. Maybe same. They can have different amplitudes, but here amplitude of the sine wave is the same, but the frequencies are different. So when you add them up, well, it looks like maybe coming from a periodic function, but it's not very easy to say what are the various frequencies, right? Well, you can, if you are careful enough, maybe you can do that. But in general, the decomposing a signal into frequencies is not easy because most of the signals are fairly random in nature. right? Random in nature, that means you don't have pure sine wave or sine waves added. So what we do then is we make a transformation of the time domain signal into so-called frequency domain signal. For example, suppose that we have 3 sine waves added here. So if I can peel off each of these sine waves from the signal and compute the energy in that signal and plot it, so I get a number here corresponding to that frequency. Then I take the next frequency. If I have a device that can take off the next frequency from this mixture and compute the energy and make a plot, I get another energy plot, and so forth. You can keep doing that until you exhausted all the frequencies in the signal, right? So then you get almost a continuous spectrum of the energy versus frequency in the signal. So invariably you have to do this. If you have a general random signal coming from an accelerometer or any sensor, and you are interested in the frequency features, characteristics of this signal, then you have to transform from the time domain to the frequency domain, right? And this is not the best way to do it. You can do it, but it's not really practical. So you need to have more advanced techniques for converting or going from the time domain to the frequency domain. Remember now, when you take data from any signal, all those data are digital data. Right? You have only discrete points of data. They're sampled at certain frequency. That's what you get. So what you have to do is you have to process this discrete data or analyze the data either in the time domain or frequency domain, doesn't matter, so that you can get the information in the signal very fast. You want to do this, if I'm doing an experiment and I want to know what the frequency components are, I don't want to wait 2 days or not even 2 hours. I want to get it right now. So you need to be able to process the information fast enough so that you can do so-called online monitoring in real time, almost in real time. Okay? Especially this is important if you are trying to transfer this information from point A to point B so that somebody can get that information very fast. Communication systems, when you are doing communication, it's real time, right? You don't wait to process the data. And I'm sure you have discussed this, right, Justin? You talked about the signal.
Yes.
Okay, so you're familiar with this. I'm just kind of recapping here. It says a vibration motion requires at least 2 components, mass and stiffness. I think the point being here is that if something vibrates, it depends on the mass of the device or the body that is vibrating, and also the stiffness. Stiffness really indicates the amount of compression or the amount of change in the length that may take place. If I have a spring, for example, and if this is sitting on the spring and vibrating, then the spring has a certain stiffness, right? Total stiffness is the amount of force required to compress or extend the spring by a unit length. So in general, most of the devices that vibrate like this, inherently they have certain amounts. They have mass, of course, and certain amount of stiffness. And the vibration frequency is somewhat controlled by those properties. And you can also have damping. Damping means if you are driving your car and you hit a bump, the car doesn't continuously vibrate, right? The vibration is going to disappear. Why is that? Because there is some damping in the shock absorbers. The shock is absorbed, and there is some device that will slow down the vibration. Okay, that's very common. Damping devices are very common. Causes of vibration, again, shaft imbalance. These are different defects in the rotating machinery. Mainly refers to rotating machinery. Okay, shaft imbalance, misalignment. We'll talk about these. Mechanical looseness, bearing problems, gear problems. Gearboxes can have problems because of problem in the gear itself, and others. inadequate lubrication or hot spots. Okay, let's see, very briefly I want to talk about some of the causes of vibration. So the first one is caused by so-called misalignment. This is the misalignment in the axis of two shafts. If the two shafts are coupled together with a coupling, by a coupling, it's possible the two shafts may not be maybe offset a little bit. If they're offset, then you have problem with something moving. And the two shafts may not intersect at zero angle. They may be slightly bent, or you can have so-called axial effect. So, or angular misalignment. So you can have misalignment in the angular direction, or offset misalignment, or parallel misalignment. So this is a better figure here. So this is an example of angular misalignment. It may be very small, but still you can have problems with the shafts not being aligned properly. So if you have angular misalignment, then when it rotates, it's going to push on the bearing. So you will see forces acting in the axial direction, whereas here you see the so-called parallel or offset misalignment. So in this case, the two shafts are here, so every time it rotates, you may have some forces acting on the bearing at 2 times the frequency, maybe sometimes 3 times the frequency. So it's more than 1 times the frequency. And you detect that frequency by installing accelerometers in certain directions. Accelerometers are the devices that you use to measure the force acting on the bearing. Depends on the direction of the force, right? The force could be acting in the axial direction, or vertical direction, or horizontal direction. So it depends. So you need to place accelerometers in general in all the 3 directions so that you can measure the vibrations coming from various directions. Imbalance is mainly caused by a little bit offset in the mass of the shaft. So if I have a shaft supposed to be uniform, but you have a little defect in the shaft, maybe some material is added to the shaft or removed from the shaft. So in that case, when the shaft rotates, you have certain force being generated, mainly like a centrifugal force coming from the rotation, that would cause the shaft, the force to be at a rate equal to the rotational speed of the shaft. And you can read up on these things. There is some discussion of the force acting on the shaft. That is the centrifugal force, mass times acceleration, right? Mass times acceleration, that's the mass. This mass is the mass of the defect times the acceleration. This is angular acceleration, right? So omega squared r times omega squared gives you the acceleration caused by the rotation of the shaft. Okay. So it depends on mass as well as the distance of the mass from the center. So anytime you change these 2 things, assuming omega is constant, the force is going to change. Higher the force, greater the vibration, displacement, or the force acting on the bearings. Some sources of imbalance, most of the time the imbalance is probably caused by manufacturing defects. Okay. Sometimes they are probably caused by humans, because I go to repair something, and I don't do the repair properly, so then I can induce certain amount of imbalance or fault in the system. So this is a list of what may be the reason: porosity, eccentricity, keys and keyways. The shafts have keys to support one piece to the other piece, loose parts in hollow places moving around, that may not be very common. Asymmetry of a rotating part, cracks in the shaft or in the device itself. So these things can cause imbalance. Operational changes, maintenance, maybe the manufacturing may be okay, there is no fault due to manufacturing, but the fault may be coming from during the operation. It could be just as you use up certain things, the parts are going to degrade. If it is a rolling mill, the two rollers are hitting against each other all the time, so they may go out of round. They're supposed to be perfectly round, right? So when they go out of round, then you will have more vibration or higher forces acting between the rollers. So those are all operation related, and they could be gradual. You don't have to see these things when you start the machinery. Maybe it takes a while before you see the vibration in these components. Mechanical looseness is caused by, it could be either coming from the way you bolt something to the foundation, or maybe there is a loose pulley, loose gear, things like that, loose belt. So these things can cause looseness in the system, not properly tightened. That would cause vibration. Okay, some terminology in the frequency domain. All right, we know what is frequency in cycles per second, or hertz. The 1 cycle per second is often referred to as a hertz. 1 hertz is 1 cycle per second. Now, if I have a shaft rotating at a certain speed, RPM, revolutions per minute, and I want to convert this into hertz, okay? What do? You divide by 60, right? Per minute, per second, you get so many revolutions per second. If the shaft speed is 1200 RPM, what is the frequency in hertz? 1200 divided by 60, or 20 hertz, right? Most of the motors, especially the induction motors that drive pumps, they may be 1200 RPM, 1800 RPM, or 3600 RPM. That's probably more common. Pump speeds, is that correct? But pump speeds roughly 1200, 1800, 3600 RPM. If you go to, pardon?
You found all those numbers out in the field, yeah.
Yeah, if you go to a high-speed turbine, then the speeds will be much higher. You go beyond 10,000 RPM, 20,000 RPM, and so forth. But most of the basic electrical devices, they probably have frequencies less than 60 hertz. Okay. Some terminology here. So let's say we know the shaft speed. That's the given speed. Something is normal operational speed. Okay. It says synchronous speed. What is synchronous frequency? Synchronous frequency is an integer multiple of that shaft speed. Okay. Multiples of the shaft speed. Integer multiples. 1 times, 2 times, and so forth. If the shaft speed is, or if a frequency, I don't mean shaft speed, if a frequency is less than 1 times shaft speed, then you have what's called sub-synchronous frequency, less than 1 times, 0.5, 0.6 times the RPM. Okay? You can have frequencies which are not multiples of the shaft speed, but some other a multiple greater than 1, a 1.5 times speed or 10.6 times the speed. So not integer multiple, but a multiple greater than 1. Those frequencies are often called non-synchronous frequencies. Okay. What are harmonics? Harmonics are integer multiples of the primary frequency, 2 times, 3 times, 4 times, and so forth. So if a shaft is rotating at a certain frequency, if you have imbalance in the system, then the frequency caused by imbalance that you see in the accelerometer is probably close to 1 times the shaft speed. If you have misalignment, it could be 3 times the shaft speed. So that means it is harmonic frequency. Harmonic frequencies are multiples of the basic rotational frequency. So you will see them in practice. Now when you get to bearing frequencies, the frequency failure faults caused by bearing faults, okay, they may not be multiples, integer multiples of the frequency. It depends on the bearing dimension, bearing number of rolling elements in the bearing, and other factors. But they are generally not multiples of the integer multiples of this basic frequency. So you may want to remember these things. What is harmonic? Harmonics of a given speed, or what is subharmonic, what is subsynchronous, what is non-synchronous, and so forth. Good to remember. Quite often in practice, instead of using frequency in hertz, folks may use this, what is called the order of that frequency. So if I take the frequency that I see and I divide that by the rotational speed of the shaft, then I get a number. So that value is called the order. Suppose say the frequency here, f, is equal to the rotational speed of the shaft. Okay, let's say 1200 RPM. And I divide that by the rotational speed, which is 1200 RPM. Then the order is 1. Right? So if somebody says the speed of this frequency, or the frequency that I see has an order of 1, that means that frequency divided by the rotational speed is equal to 1. In other words, it's equal to the rotational frequency. If the order is 10, then the frequency that you see is 10 times the rotational speed. So it is just a terminology used quite often, okay? Because it's somewhat easy to understand instead of using hertz or other quantities. Easy to interpret or follow what's going on. Quick examples here. It says the speed of a primary pump is 1182 RPM. Okay. The frequency is, if I want to convert this into hertz, divide by 60. So that is the rotational frequency of that main shaft. Frequency of one order is same as this. Okay, if you have frequency 9.85, that is 0.5 times the order, right? Frequency of 10 times the order, and so forth. So you can read those numbers. It's kind of interesting. This number here it says pump frequency is 1182 RPM. If the pump is driven by the induction motors have what is called no load speed. If I run the motor with zero load, of course there's always load, then it has a standard speed that's called the no load speed. So the no load speed of this pump is probably 1200 RPM. So as you load the motor, that means as you start the pump, the motor has to do work to pump the water, right? So the speed of the motor will go down a little bit. Okay, induction motors have the property of they gotta slow down, otherwise they can't generate enough power. So the speed, the main shaft speed will decrease a little bit. In this case, let's say it's 1182 RPM, which is 19.7 hertz. So if I take the difference if I take the difference between the no load frequency, which is 20 hertz, right? 20 hertz, and